Hello friends, so in the last 4 videos we have seen that is regarding nucleophilic substitution reaction, different types of mechanism. All the links are given in the description box, and today in this video we will discuss some problems or examples based on all those mechanisms. So before that, let's quickly brush up the main point of difference between the SN1 mechanism and SN2 mechanism. So kinetics, the rate expression for SN1, it is rate constant into the concentration of the alkyl halide only, and for SN2 there is concentration term of alkyl halide, that is our main substrate, as well as the concentration of the incoming nucleophile. For now, different types of substrate: primary, secondary, tertiary. So for primary, SN1 we hardly observe, but it is good for SN2. Secondary alkyl halide, it is moderate for both. And tertiary alkyl halide, it is good for SN1, but we hardly see any mechanism in SN2. Now see, for secondary alkyl halide, it is moderate in both cases. Why? Because for SN1, as we move from primary to tertiary, because of the stability of carbocation, the reaction rate is gradually increasing. On the other hand, in SN2, if you move from primary to tertiary alkyl halide, it falls down. So secondary alkyl halide, it is always in between primary and tertiary halide in both cases. So that is the reason you will find SN1, SN2 for secondary alkyl halide, that is moderate. Then if we look at leaving group, it should be less basic in both cases, because again see, at the rate expression our leaving group is always there. So if it is less basic, that is X minus, if it is very stable, then only it can act as very good leaving group. Nucleophilicity, it is not important in case of SN1 because there is no such term involved in rate expression, but here it is important. Preferred solvent, we have discussed in detail that in SN1 it should be polar protic solvent, but in case of SN2 it should be polar aprotic solvent. Then what about the stereochemistry? Here we observe racemization in SN1 because there is intermediate carbocation intermediate, which is planar configuration, and the nucleophile can attack from both sides. So 50% chance of both the stereochemistry, but in brackets it is written that more inversion is possible. So why it is so? Because suppose the rate of breaking this bond, it is taking some time. So what will happen? In spite of the fact that carbocation is our intermediate, but still if the bond, if the time for the, it is taking large time for breaking of the bond is between R and X, then there will be more chance that nucleophile, it will attack from the opposite side. So it can happen that more inversion possibility is there. So that may happen. But if the stability of R plus and if Rx bond is breaking at a very faster rate, then you can expect racemization. And in case of SN2, it is mostly inversion. It is also known as Walden inversion. Rearrangement. Rearrangement is very common for SN1 but not for SN2. Why? Because rearrangement is possible only for carbocation intermediate, and carbocation intermediate, it is involved only in SN1. So that is why rearrangement it is observed. So that is all about the main difference between SN1 and SN2. Now come to the problems. So our first problem is the following bicyclic compound is unreactive towards nucleophilic substitution either by SN1 and SN2, both. So in both ways it is not possible. So let's first see why by SN1 it is not possible. If it is SN1, the carbocation will be generated here, that is at the bridgehead position. It will be generated here, isn't it? So as a result, what will happen? This cannot attain planar configuration, so it will be very unstable. So that is the main reason that it is unreactive towards SN1 reaction. Bridgehead carbocation formation is not possible, and even if it forms, it will be very unstable. So that is the reason that SN1 mechanism is not possible. Now what is the problem in SN2 mechanism? Now for SN2 mechanism, the nucleophile, it will attack from the opposite side of bromine. That is our leaving group. So that is also sterically very problematic. So backside attack of the nucleophile on the carbon bearing the bromine atom, that is sterically prevented. So that is the reason that SN2 mechanism is also not possible for this structure. Now come to the second problem. Neopentyl chloride cannot be prepared from neopentyl alcohol by the following reaction. So this is our neopentyl alcohol, that is Me3C CH2OH, and this is our product, that is the expected product. So why it is expected product? Because just OH will be replaced by Cl, so you will get this product. So this is our expected product. But why we cannot prepare, so that we have to see. So in presence of HCl that we are using as reagent, this OH will be protonated. So now it will be OH2 and H2O will be removed. So after removal of water molecule, there will be a positive charge. Now this is a primary carbocation. So there will be some rearrangement. So what is the rearrangement? Here the methyl group is shifting towards this carbocation, and as a result you are getting this new intermediate which is more stable because it is now tertiary. Now the Cl will attack at this carbocation and you will get some another product which is tertiary amyl alcohol. It is not our expected neopentyl chloride. So neopentyl chloride, it will be formed only if it is attacking at the initially formed carbocation, which is 1 degree. But as there is rearrangement taking place, so that is why we are getting tertiary amyl chloride, not this one. So this is the reason that neopentyl chloride we cannot make from neopentyl alcohol by this reaction. Now that is all about SN1 mechanism. Now what will be the problem if it is SN2 mechanism? Because it is primary, our substrate is primary, isn't it? Because OH is attached to carbon. So this is primary, but still we will see that there is some problem. Now what is the problem? If you look at the mechanism mentioned in the box, when chloride, it will be attacking at this carbon which is carrying the leaving group OH2, there will be some steric problem. So because of steric reason, SN2 mechanism is very slow. So though we know that for 1 degree substrate in SN2 mechanism, the reaction should be very good, but still because of this neopentyl group which is present here. Okay, so that is the reason in spite of being 1 degree starting material, we will not have SN2 mechanism in this case. So even if it is S1 or SN2, in both cases we cannot get this product. So in SN1 mechanism you will get something else. You will get some product, but it is not the expected product. And in SN2 there is no reaction happening at all. Fine. Next come to the third problem. Chloroacetone undergoes SN1 reaction faster. That is undergoes SN2 reaction faster than in propyl chloride. But if you consider SN1, then reverse is the case. So first we have to see what is the structure of chloroacetone and what is the structure of N-propyl chloride. So N-propyl chloride, it is very simple structure, CH3 CH2 Cl, linear structure. And what about chloroacetone? Acetone structure we know, CH3CO CH3. If you replace one of the hydrogen from any of the methyl group, just replace one of the hydrogen by chloride, then it will be chloroacetone. So this is the structure of chloroacetone. Now the nucleophile is it should attack here, but before that this type of transition state will be formed. There is a CO group just beside this carbon, isn't it? So as a result, what will happen? This negative charge, it will spread over all of this region. So it will be very stable, because we know if some charge is localized at a particular position and just compare the same situation that the charge is delocalized, it is spreading over a large area, then what will happen? It will be more stable. So this is the transition state which is very stable. So that is the reason that chloroacetone undergoes SN2 reaction compared to N-propyl chloride. It will be very fast. But now if you consider SN1 mechanism, the opposite is the case. Opposite is the case means now N-propyl chloride will react faster than chloroacetone. Now what is the reason? Because in N-propyl chloride and just compared with chloroacetone, the carbocation that will be formed in case of chloroacetone, that is at this position, it will be very unstable because there is an electron withdrawing group present just beside it. CO is electron withdrawing group. So electron withdrawing group CO, it will destabilize the carbocation. And whenever there is destabilization of carbocation, activation energy will be very high in case of SN1. So SN1 reaction, it will be faster in case of N-propyl chloride. Come to the fourth problem. Halocyclohexane reacts slowly towards SN1 reaction. Now halocyclohexane means just imagine the structure of cyclohexane, and one of the, that is CH2, one of the hydrogen, if it is replaced by any halogen, then this is halocyclohexane. So this is our halo group. Now see, this is equatorial, isn't it? But halocyclohexane, if you draw, this is the general structure. It may be, this is halocyclohexane. Now this X group, it may be in equatorial position or it may be in axial position. Now the picture that is shown here, in this case X is equatorial position. So halocyclohexane undergoes SN2 reaction in a much faster way through equatorial conformation. Cyclohexane undergo SN2 reaction via the relatively stable equatorial conformation. You can also think about the another axial conformation, which is like this. Now if you compare this structure with this structure, the equatorial one, that is the relatively stable, that always undergoes SN2 reaction. So that is why I have drawn only that. Now there is 2 hydrogen at 3 position and 5 position. So suppose if it is 1 position, this will be 2, 3, 4 and 5. So the axial hydrogens at C3 and C5, it will interfere sterically with the attacking nucleophile. So this is our attacking nucleophile, and there is some steric hindrance which is shown by green line. So as a result, what will be the case? The transition state, it will be very unstable. So that is the reason that halocyclohexane, they reacts very slowly towards SN2 reaction. Next problem. Chloromethyl methyl ether. So it is actually a derivative of dimethyl ether. Dimethyl ether means MeO-Me, that is CH3O-CH3. Now just replace one of the hydrogen of methyl group with chloroatom. It will be chloromethyl ether. Chloromethyl methyl ether. So if you consider oxygen, on one side there is methyl group and on another side there is CH2Cl group. So chloromethyl methyl ether undergoes SN1 reaction at a very fast rate. Why? So see, just you have to think about the carbocation. If you break this bond, there will be carbocation formation over this carbon. Now this carbon, at a first glance, it seems that OMe, it is electron withdrawing group because oxygen is very highly electronegative atom. So this carbocation should not be very stable. But actually here another process is happening. What is that? The lone pair over oxygen is actually stabilizing this carbocation by formation of this type of structure. So though it is primary carbocation, and though there is a amino group present, which at a first glance we may think that it should destabilize the carbocation, but actually it is a resonance stabilized structure, okay, that we are getting here. So that is the reason that chloromethyl methyl ether, though the carbocation is primary, but still it is giving very fast reaction. Next problem. So here we have a bicyclic structure, and you can see there is a OMe group attached. Then we are using HBr. We are getting this product, and another byproduct is MEBr. So how we are getting this type of product, that we have to explain here. So first we will see if it is going through SN1 mechanism, then what will happen. So the carbocation that we will get, that is at this bridged position. Again, it cannot attain planar configuration. That is its demand. That is, it is sp2 carbon, the carbocation. So as it is not stable, so through SN1 mechanism, the reaction cannot proceed. Next, we have to see what is the problem if it is SN2. But before that, here the R prime group, it is actually, suppose this bicyclic structure, that is the group which is attached to the oxygen, suppose it is R prime, and the methyl group, suppose it is R. So why I have written it so? Because now I will write the structure as R prime O R, so that it will be in simpler form. So see what is the structure now, R prime O R. So this is our R prime, then we have oxygen, and this is R. So I have written it in a simple form. Now we are using HBr, so the oxygen will be protonated. See, the oxygen is protonated. Now the Br minus which is left out, you can think that Br minus, it can attack on the methyl group that is present here in the right hand side. But you can also think that why it is not attacking at the R prime. Now to attack of the Br minus, it is easier on methyl carbon rather than on this carbon because of the steric reason. So that is why Br minus, it will attack at this carbon, and you will get RBr, which is nothing but MEBr. And this bond will be broken. So what you are getting? You are getting R prime OH. So R prime OH is basically this compound. Okay. So this is the mechanism that is happening in SN2. Our normal expectation is that OMe will be removed, and that place that will be taken by Br. So that we may expect that it should be the product, but actually that is not the case. So whenever you are getting this type of bicyclic structure, because there is some structural problem, so we have to think it in different way. It is always better you write the structure elaborately, and then you try to see that from which side the attack of the nucleophile it will be easier. Then only we can reach correct conclusion. Okay, so today we have discussed total 6 problems. In the next video, this problem discussion, it will be continued. In the next video, I will also discuss some more of the problems. Okay, so if you find the video helpful, please like, share and subscribe. Thank you for your time.